Hello and welcome to this very simple tutorial on column buckling. The idea of this tutorial is to show you different buckling modes for a column, lateral buckling and torsional buckling, and how you can model that in unbraced 3D. Unbraced 3D, first objective is to model bridges, but you can also use it to model columns and study different types of stability issues, whether column buckling or beam buckling. So here's an example on column buckling. If you go to features, you'll see that I have, of course, pin and roller supports, different type of boundary conditions that I will explain in a minute. I am applying a uniform compression on the column by using point loads. I've got stiffeners on both ends of the column, and I'm also running an eigenvalue buckling analysis. Erection analysis here. This is not, technically speaking, an erection analysis. I'm not erecting a bridge. It just means that there's no concrete on top of the system. It's just a steel. It's just a steel structure. The column is 60 foot long. The material properties for the steel are the default ones. I've got two supports for the column. I've got a pin at 0 and a roller at 60 foot. So you can click this button every time you have a doubt. 1 means a pin and 0 means a roller. I've got stiffeners at both ends of the column on both sides of the web. This is why I have a 3 here. The stiffener on both sides of the web, select 3. The thickness of the stiffener is here, as well as the width here. I do have an additional boundary condition or special fixity. This is because by default, the software will not restrain the longitudinal displacement at the top flange node for pin or roller supports. So here for the column, I do need to restrain that. Otherwise, the boundary conditions would be wrong. So I need to restrain the y direction, the y displacement, or 2 here, of that number 8 node. So direction 2, location 8, at the start of the column. And here I don't need to click on this button because the model is already set up, but it doesn't do anything. It doesn't do any harm to click on it again. Let's see what it does. What it does, it looks at all the reference points on the bridge, on the column here. So I have just 0 and 60, so just one segment. It's an extremely simple example. And here you can see it's a very fine mesh. Remember that the elements are quadratic. And I'm also using this very fine option here to have 8 elements through the web depth. You can choose either 4 or 8. I can have this luxury here because it's a very simple and small model, so why not? It will give me slightly more accurate response answer on the eigenvalue buckling modes. These are the cross-sectional dimensions of the column. You can look at this image in case there's any doubt on what is meant with the web depth, for example. I am assigning this profile to the one segment that I have, of course. I am activating the whole length of the column, so from 0 to 60. You would typically use this form for an erection sequence for a longer bridge, of course, but here it's just saying, hey, we're activating the whole length of the column. And we also have 4 point loads at the ends of the column. Because I am applying a uniform compression, I'm using 2 and 8 in the direction 2. So what is meant again is that I'm applying 0.5 kip at both these nodes in the direction 2, so the longitudinal direction at 0 foot and 60 feet. along the length of the column here. This is to apply uniform compression. I am not turning on the self-weight of the column because I just want to see the eigenvalue, what's the buckling capacity of the column under just a uniform compression. And here, this is the form where you set up the eigenvalue buckling analysis. I did hit this button here, advanced, because by default, the search interval for the eigensolver would be between 0 and 10, but I know here, I've run this model before, you would need several iterations before finding the eigenvalue buckling, the buckling eigenvalue, which is actually much higher. So let's go up to 300. You don't need to click on this button, it's just a shortcut here, because otherwise the solver will go through several iterations until it finds an eigenvalue. And then let's hit run. So now the eigensolver is running. It has found the different eigenvalues. Let's zoom in. Let's check the plate thicknesses. This is a really nice way to check your model. You can see it's a really fine mesh. And let's look at the mode shape. So this is the first mode shape of the column. And by the way, let's look at the boundary conditions here. You can see I'm restraining all these displacements. Here on that end, it is free to move. I am applying a uniform compression on the column. You can see the green arrows, which are showing the loads. So this column is under pure compression. Let's look at the buckle shape. It's a lateral buckling mode. In case there's any doubt whether the column is buckling in the strong axis or in the weak axis, you can just go to this view and you will see here that of course it is buckling in the weak axis, of course, if there's any visual confusion from this figure. Now let's look at the second mode shape. Second mode shape is actually also a lateral buckling mode, but it's a sine wave like this, so it's a higher buckling mode. The third buckling mode is a torsional mode. It's again a higher mode. So this is, and if you check these eigenvalues with the Euler buckling, etc., you would find very similar results. Now let's see what happens if we brace the column at the third points. So let's go back to reference points and add some springs there. So let's add 2 springs at the third point, so that's going to be 20 and 40 feet along the girder. Location on the cross section, let's use just the mid-web node, so 5. Stiffness, let's use 10 kip per inch. And direction is the transverse direction, so it's X, so 1 here. This is lateral, discrete lateral bracing that I'm defining. Next, I'm not changing any of this, but now because I've added 2 points at 20 and 40 feet, I need to click on this button. Otherwise, the mesher will have difficulties finding the nodes where to define the springs. So I need to click on this button. And you will see that now I have 3 segments instead of 1. I am keeping the same mesh size, 6 inches. Profile hasn't changed and the assignments are still the same. It's a uniform column. This, of course, does not change. This form here is new. I've defined some springs, so I need to say whether they're active or not. And I also have a column here where I can say, hey, instead of 10 kip per inch, I well, I really want to apply 20 kip per inch, so I can go here and enter 2, but I don't need to do that here. 10 kip per inch is higher than the ideal stiffness here, so it's okay. Point loads are the same, so none of this has changed. And now let's run the eigenvalue buckling analysis again. So just one mode. You can see the springs here, which are bracing the column laterally. Let's look at the buckled shape. And as expected, the springs are effectively bracing the column laterally, so the first buckling mode is the torsional mode. So I hope you have learned how to define springs in this tutorial, how reference points are defined, and how you can use this to study column stability. Thank you.